Good evening once again to everyone. I trust we are doing very, very great. As we announced on our Google Classroom and on our WhatsApp, in today's session, we are looking at microcontrollers. We are looking at how they communicate, and we're also going to do a little bit of an introduction to microcontroller programming. You've made all of you here, Bernard, Felix, Herbert, Isaac, Samuel, everyone, you've made very, very good, very, very great progress from the start of the program, from session one, session two, session three, session four, session five, all the way up to session nine, which happened last week. And so far, with regards to electronics and programming, even with our run before you walk sessions, you learned how these microcontrollers work. If you take a microcontroller off of a PCB, a printed circuit board in a computer or in a TV that is destroyed, you can just take one of the microcontrollers on that board, and right away you can just look up the name on that particular microcontroller, and you just Google it, or you use these AI models like Copilot or ChatGPT, and then you tell ChatGPT the name of the microcontroller, right? The name that has been written on the microcontroller. And usually they are very, very tiny, and so you'd want to just turn on your phone's torch. You just get a little bit amount of light on it, and then you just get it a bit closer to your eyes, and then you look at the name, that tiny name that has been written on the microcontroller, and then you just search for the name. Immediately you search for the name, you're going to have some data. You're going to have some information about that particular microcontroller, and we've referred to that as data sheet, right? So you can, just like Samsung phones or iPhones, these products are made by companies, and in order for you to use those phones, or to use any appliance, right? If you buy a computer from Dell, if you buy a computer from Lenovo, if you buy a computer from Apple, they are obviously going to give you some instructions, some information about the product that you are going to be using. If the product needs to be put on a table, they are going to write in the document that, hey, you are supposed to put the computer on a table. You're not supposed to put it on the floor. The computer, you need to plug it into a socket that gives a voltage of, let's say, 240 volts. Do not give it a voltage that is above 240 volts. So all of these information, we find them in a data sheet. That's a document that is found in that's a document that the manufacturers of the components. So if you're working with a microcontroller, it's going to tell you that, hey, you need to give it an input voltage of this. You need to connect it to this, right? If you need to connect a capacitor to it, connect a capacitor of this to it, a capacitor of this value to it, connect a resistor of this value to the microcontroller. The microcontroller has 13 pins on it, or it has 6 pins or 8 pins on it. And all of these pins, there is one pin called serial clock. There is one pin called, there are 15 input output pins. All of those things. The data sheet is going to tell you about it. So you've made some very, very good progress. Everyone in here, you've made some very good progress on your robotics journey. And right in last week's session, we did a little bit of an introduction to electronics, and we took a look at 10 electronic components that whatever printer circuit board, or whatever board you find in a product that exists, like in your computer. If you open up your computer, you're going to find these 10 components on that computer's board. If you open up a phone, you're going to find all of these 10 components on that phone. If you let's say if you buy an AirPod, and you open that AirPod app, and then you look on the electronics board in the AirPod, you are going to find those components, those 10 components on there. And if you buy, let's say, a watch, or if you buy, anything electronics you buy, you're going to find all of these 10 components on there, because they are foundational, right? They are like every board you're going to buy, every electronics board, they are on there. And yes, we took a look at an LED. We know an LED is so common, right? And so that's why we started from looking at an LED. We also took a look at a battery. A battery is a source of energy, and so we feed it. We send the energy from the battery into the LED to turn it on and off. And we used an example that everyone here appreciates, right? In those old television that we used to use. Usually when you press the switch, there are two LEDs on there, right? There are two lights on there, green one and red one. If the TV is off, you have the red one turn on. If the TV is on, you have the green one turn on, right? So those were LEDs, and then battery, source of energy. And then we took a look at a switch, and then we took a look at yes, the switch is so common. We used to turn on or turn off. And then we took a look at a resistor, and we got to know that, hey, sometimes you have a huge battery, a battery like, let's say, a 9-volt battery, but a component like an LED, if you supply that 9 volt into the LED, you may burn it, you may destroy it. And so we use a resistor so that resistor can resist some of the current or some of the voltage from the huge amount of voltage or the huge amount of energy going into the LED to destroy it. Great. And we also took a look at a capacitor. And we got to know that for a capacitor, it's just like a battery, but it stores a tiny amount of energy. And while a battery can be able to power an LED for like 4 hours or 3 hours, when you connect that battery to an LED, the LED is going to turn on for like 4 hours. But for a capacitor, it's just a few seconds, right? It's just a few seconds. Even though it has some amount of energy stored in it, it's not like a battery. It's not so strong as a battery. It cannot power the component for a very long time. And so what we tend to use a capacitor for is when our power source is not stable, like we have a 9-volt battery, and the battery has some amount of fault in it because of the manufacturers, right? The manufacturers didn't do a good job. And so when you connect this capacitor to an LED, instead of the battery supplying 9 volt into the component, into the LED, you find that the battery is unable to give a consistent 9 volt into the LED. So at one point in time, it's giving 9 volts. At a certain point in time, it goes down to 8.9. And then it goes up to 9 volt again, and then it goes down to 8.9, 9, 8.9, 9 volt, 8.9 volt. We do not want that increase and decrease in voltage, and we refer to that as spikes or noise. In electronics, we call it noise or spikes, right? So if you are building a very good product for people to use, if you are buying a product, if you are building as an engineer, you want to build a remote controlled, let's say a remote controlled product, and you are going to sell it to users, you do not want these increase and decrease in voltage to destroy your product, right? Otherwise your customers are going to leave the product. So that's a capacitor. You just have to connect a capacitor there, and the capacitor has positive and negative terminal. So all you have to do is just connect the positive of the capacitor to the positive of the battery, negative of the capacitor to negative of the battery, and you have the capacitor stand in between the LED and your battery. So it's standing in the middle. And what it's going to do is that it's going to say that, hey battery, I know you have on and off problem, like you go up and then you go down. So what I'm going to do is I'm going to store the 9 volt you are giving me. So at a point when you have 9 volt, I'm going to store that 9 volt, so that at a point when you go down, I'm going to supply equal 9 volt into the LED. So the capacitor makes sure that it stabilizes the voltage to avoid the increase and decrease in voltages. Good. So that was a capacitor. That's just an introduction to a capacitor. When we go forward, we're going to be appreciating it. And then we looked at an inductor. And we got to know that an inductor is it does the same job as a capacitor, but it manages current, right? So it makes sure that the current is smooth. So in the same way, sometimes you want a smooth amount of current to go into your LED or your component, but it can, let's say your component requires 250 milliamperes of current, right? But at a certain point in time, it goes to 214, 215, 214. It goes up and then it comes down. But you do not want your current to increase and decrease, right? You want a consistent amount of current. And so what you do as an engineer is you use an inductor. You just have to connect an inductor in your electronics circuit. And what an inductor is going to do is it's going to store some current, right? We are going to be going into detail how it works. But I believe everyone here, if you are studying electronics and electrical engineering, or you're studying computer science, computer engineering, everyone in here has heard about an inductor. You've learned a little bit about electronics, and so you know about an inductor. But yeah, and so the theoretical aspect of an inductor is it has some coils in there, right? And it has been the coils, that the copper wire coils have been wound around a certain material. I do not remember what material can someone contribute? What material is the copper? This is not necessary. Once we go off today's session, everyone, you can just do a little bit of a search on how inductors are made, right? It's so simple. Just copper wire wound around a certain material, and once current goes through it, it creates a magnetic field, right? And we do not need to go into detail. Everyone, right after, as engineers, we figure things out, we learn about things, we read about things. And so once we go off today's session, everyone, just because you're an engineer, just read about an inductor. But the practical aspect is what we are taking care of, right? Everyone here wants to be able to appreciate all of these components, how you can build your own printed circuit board, and that's exactly what we are focused on. So after talking about an inductor, we just went on to a diode, and we learned that a diode allows current to flow in only one direction. And we got to know that in Tinkercad, we just did a little bit of a connection, and we got to connect an LED, right? An LED through a diode to a battery. And we got to know that for you to allow the current to flow in only one direction through the diode, you need to connect the negative terminal of your battery to the negative terminal of the diode. So if you connect your negative of your battery to the negative terminal of the diode, the diode is going to say, hey, you've done the right thing, and so I'm going to allow current to flow through me. However, if you connect the negative terminal of your battery to the positive terminal of your diode, it's not going to allow current to flow through it. But once we go forward, everyone here is going to appreciate what a diode is used for, how we use it, how we can use it to protect some components, right? And how in electronics sometimes there is a backflow of voltage or current, and that may destroy other components. So we use a diode to do it. Well, we're all going to appreciate that. Right after talking about a diode, we looked at a transistor, and we mentioned that for transistors there are two types, right? There are two types. We looked at MOSFET and bipolar junction transistors, which are simplified as BJTs, right? B stands for bipolar, J stands for junction, and T stands for transistor. So BJT, right? So bipolar junction transistors, BJTs. All right. So under transistors, we have two types: MOSFET, and we have bipolar junction transistors. And we know that for transistors, they have just three terminals, right? We have learned that they have just three terminals. For the MOSFET type, it has the drain, it has the source, and has the gate terminal, right? The source terminal, the drain terminal, and the gate terminal. And then for bipolar junction transistors, or for simplified as BJTs, they also have three terminals. Their terminals are emitter, collector, and then base. And we have understood what these terminals do, right? We have understood that these terminals, they are nothing. They have different names. It's like when you go to the town of MOSFET, it's called a terminal may be called source, right? A terminal is called source. When you go to the MOSFET's town, it's called source, right? But when you are looking at it in terms of bipolar junction transistor, it is rather called emitter, right? And when we looked at it, and everyone here appreciated it, right? We got to know that the source terminal, we connect our battery to it, because our battery is the source of the our battery our battery is the source of the energy, right? And for bipolar junction transistors, we also got to know that it's called emitter. That terminal is called emitter, and because the emit the battery is the emitter. The battery is what will be emitting the energy. So source for MOSFET and emitter for bipolar junction transistor, they do the same thing, they just have different names. Right after we talked about that terminal, that first terminal, we went on to the second terminal, and the second terminal is called drain. For MOSFET, it's called drain, but for bipolar junction transistors, it's called what is it called? It's called collector, right? So for MOSFET, it's called drain. For bipolar junction transistors, it's called collector. They do the same thing, it's just different names, right? So collector for bipolar junction transistors, and for MOSFET, it's called drain, because and you connect something like an LED or a motor to it, components that drain energy, components that collect energy, and so that's why it's called collector, and that's why it's called drain, right? And then finally we looked at the last terminal called gate terminal. Gate terminal. So on a MOSFET, it's called gate terminal, but for a bipolar junction transistor, it's called what is it called? Base, right? And gate terminal, base terminal, they are all the same. They do the same work, but it's just that the names are different. So drain, no, gate is the same as base. And how we got to link them together is that is just what they do, right? So for a transistor, we've already taken a look at the two terminals, right? Drain, collector, emitter, source. We've taken a look at those two. You connect the source of your energy to one. You connect the component that will be taking the energy from one. So source, and then the one that is going to take. After connecting it, you need to turn the transistor on and off. And you turn the transistor on and off by sending some signals into it, by sending some voltage into it, right? By sending some current into it. So voltage and current. We've already, I believe everyone here has taken note of it, that in electronics, when we mention signal, for now, when we mention signal, we are referring to voltage and current. So these two things, they can be used when you say signal. Ask the person, hey, which type of signal are you referring to? Is it voltage? Is it current? So voltage, current, that's what we refer to as signal. So after you have connected your battery and then your component that will be taking energy from the battery to your transistor, you have just one terminal left, and that is where you send your signals into. So you say, hey, transistor, turn on, by sending an on and off signal into that particular gate terminal or base terminal. And we did something that will help us remember. For bipolar junction transistors, it says the base, right? It says it's called the base terminal. And we got to remember, and we got to understand that it's for us to understand, it just says base, right? So understand it this way, that you need to turn the transistor on based on a certain current or based on a certain voltage, right? But yeah, the actual correct one is based on a current. And by the end of the at the end of the session, we I think we made this clear that for MOSFETs, they work on the principle of voltage, but for bipolar junction transistors, they work on the principle of current. And so if you're working with bipolar junction transistors, as engineers here, Benedict, Agnes, Bernard, Felix, Herbert, Abdul Salam, Isaac, in team, Samuel Entry, as you are working together as engineers designing your printed circuit board, when you are working with bipolar junction transistors, everyone here, you're going to be asking yourself, hey, how much current did you send into the bipolar junction transistor? How much current did you send into the bipolar junction transistor? But if you are using a MOSFET, The language you use is how much voltage did you send into the MOSFET. So I believe everyone is good. This was just a quick revision. After we talked about a transistor, we went on to a voltage regulator, and then we got to know that voltage regulators, it's so simple. Voltage regulators, it's just that sometimes when you have a 9-volt battery, a huge battery, like a 9-volt battery or a 12-volt battery or a 24-volt battery, you do not want to use the 24, you do not want to work with the 24-volt battery, that huge voltage. And so what we want to do is, let's say your microcontroller requires 5 volts to work, or your LED requires 5 volts. Your LED may require 3.3 volts to work. And so what you do is you use a voltage regulator. So there are some voltage regulators that are rated 5 volts, right? And they will tell you that, hey, the input of this voltage regulator, it can take a huge battery of, let's say, 7 volts to 12 volts, and it's going to step that voltage down to a desired voltage, right? So you use a voltage divider, use a voltage regulator to step down voltage. So if you have a 9-volt battery but you want 5 volts, all you have to do is just connect that 9-volt battery to a regulator, to a voltage regulator. And the voltage regulator is going to step down that voltage to an output voltage of, let's say, 5 volt or 3.3 volt, that output voltage that you want. So that was voltage regulators. And then lastly, we took a look at integrated circuit, IC, integrated circuit, and we got to know that integrated circuits are just those black components that have multiple pins. So they may have 6 pins, they may have 8 pins, all of those. Any component on a board that has multiple pins, they are just called integrated circuits. And so like the microcontroller we took a look at in our introductory sessions, it had 8 pins, right? And so that is considered as an integrated circuit. So just like the name goes, integrated circuit, lots of circuits that have been fused or integrated into a very tiny space, right? So that's it, integrated circuit. So every black component you see on a board, on a printer circuit board, on an electronics board, those black components with multiple pins, those black components with like 6 pins, 8 pins, 16 pins, those multiple pins. Some have 40 pins, some have a lot of pins that you may even find difficult counting, right? So yes, those are integrated circuits. And yeah, we took a look at the examples of integrated circuits. Microcontroller. A microcontroller is just an example of an integrated circuit. And then we also took notes that integrated circuits, they perform specific functions, right? Like a microcontroller, we write our code. The microcontroller acts like the brain of our board. And so after writing our instructions, let's say we say, hey, we want you to turn a motor on, we want you to turn a light on, we want you to send wireless signal to a certain component, we want you to do this, we want you to do that based on a product that we are building, like an airport. You open up your airport, and then you take the airport out, and then it turns on automatically, right? And then it connects to a computer, it connects to a phone. So we write all of those instructions. All of those instructions go onto a tiny, it goes onto a microcontroller, and that microcontroller is going to think. It's going to act as the brain of our system. So that is it. That's a microcontroller, and yeah, my integrated circuits, they perform specific functions. And so we may have an integrated circuit like a certain component called TP4056, TP4056, and that is a charging component, right? It's a charging IC, it's a charging integrated circuit. It performs a specific function, and its function is charging. And so whenever you buy these what is it called, power banks. Yes, whenever you purchase a power bank from a store and you use your power bank to charge your phone, you charge your phone, but you do not know the components found on that in that particular power bank's board, right? The power bank's electronics board, it has this particular micro integrated circuit called TP4056. I think let's take a look at it. TP4056. Let's quickly take a look at yeah, let's quickly take a look at this TP4056. We took a look at it in our previous session, but yeah, let's appreciate it a little bit. Good. In just a second, let's take a look at how a TP4056 looks like. Okay, let's see if we are finding some images here. Looks like Google is giving us some. Okay, I think we found a component here. So yeah, let's take a look at TP4056. All right, good. TP4056. All right, so let's take a look at TP4056. I believe it should pop up in just a second. I believe everyone can see it. Yeah, so that is TP4056. Whenever you buy a power bank, all right, that's great, Bernard, Herbert. All right, that's great. So whenever you buy a power bank, this particular IC, this particular integrated circuit, it has multiple pins. It has 8 pins on there. So the manufacturers, the Chinese companies that manufacture, or the German or the US companies that manufacture these power banks, they use this integrated circuit, this IC, and it's going to get connected to the battery in a power bank, the lithium ion batteries in a power bank, and it's going to get connected to the input voltage, the 5 volts that is charging it, right? From the socket or from the charger, and it's going to receive an input voltage, and then it will regulate that input voltage, and then it will use that voltage to charge those batteries in your power bank. So that is the TP4056. It's just an example of an integrated circuit. As we have mentioned, integrated circuits, they perform specific functions. Microcontroller, we write our code onto it, it acts as the brain. TP4056, it's a charging IC, it's a charging integrated circuit, it's responsible for charging. And I remember in our previous session, we also mentioned that we also have it's an integrated circuit, or an IC, that is responsible for controlling motors. So if you want a motor to move clockwise and anti-clockwise, if you want to be able to control the speed of the motor, there are several integrated circuits that perform that function. So we've made everyone in here. You've made some very good progress on your robotics journey. In electronics, you've made some very good progress with these 10 components: LED, battery, switch, resistor, capacitor, inductor, diode, transistor, voltage regulator, integrated circuit. Which under integrated circuit we have microcontrollers, TP4056 for charging, and all of those ones. You've made some very good progress. All right, now let's go into today's session. Our session is going to last 40 minutes, right? Like everyone has noted. But we started from 8:05, and so we're going to be ending at 8:45. But today's agenda is so simple. We're going to be looking at already in our introductory sessions, we've taken a look at microcontrollers, and so it's going to be easier. Like we mentioned, whenever you hear something for the first time, it may sound strange. You may not really understand it. You may not really appreciate it. But when you hear it on the second time, then it becomes easier. And so that's what we hope for in today's session. All right, let's go into let's take one. Let's take so microcontrollers. We know that microcontrollers are the brain, right? So that's out of that's out of the equation. Now let's take a look at two microcontrollers that we are going to be using in today's session. One is the microcontroller that's found on the Arduino board, and the other is the microcontroller that tiny microcontroller we took a look at in our called the 80 tiny 85 microcontroller. So these are going to be the two microcontrollers we are going to be using in today's session. Um but yeah, and so let's quickly go into our let's quickly go into um tanker card, and let's take a look at these microcontrollers first, and we'll just take a look at their pin out, right? Their pin out. Everyone, please take note of the word we just mentioned, pin out. Let's put it here in the chat. um okay okay, let's put it here, pin out. So it's just PINOUT, pin and out. So pin out, microcontrollers have pins, right? microcontrollers have pins, and we talked about the pins, right? It may have lots of pins, but even before we proceed, let's make sure everyone is here and paying attention. Let's make sure everyone is here. Give me a thumbs up if you are here. Agnes, Benedict, Bernard, Felix. Okay, all right. Felix, Herbert, Abdul Salam, Isaac, Intim, Michael Opoti, Samuel Entry. I believe everyone is here. All right. That's great. That's great. All right. So yeah, let's proceed. So we're taking a look at two microcontrollers. The Atmega 328, and that is the microcontroller that is found on an Arduino board. So yeah, let's go into this. Yeah, let's use this setup here, our previous setup, and yeah, let's leverage on this, make some good progress. Let's just give Tinkercad a few seconds, and it will be done loading. Wow, Tinkercad is taking some time, but yeah. So on an Arduino board, and everyone here appreciates what an Arduino board is, right? In our introductory sessions, we took a look at an Arduino board. This is an Arduino board. Let's bring it in here quickly. Where is it? Yeah, this is an Arduino board. It's found in your SIR kit. It's found in your simplified introduction to robotics kit. You have so many microcontrollers in your kit, and once everyone receives it, you're going to see this. And this may not be the first time. This may not be the first time. Some of you are seeing an Arduino board. Some of you have already done a little bit of robotics, right? But yeah, so this is an Arduino board. It's just like a board. It's like the board found in your computer, or when you open up your laptop, the big green board that you see. This is just a blue one, right? So this has a microcontroller on top of it. And yeah, so this microcontroller here, this is a microcontroller. I believe everyone appreciates that. This is a microcontroller. This is the brain, and it has been soldered. It has been put onto this board, and other components have been equally put on the. So yeah, that's that. This is an Arduino board, and this is the Arduino microcontroller. And the actual name of this microcontroller is Atmega 328. ATMEGA. That's Atmega, and 328. Right, so that's the name of the microcontroller. And then let's bring in our second microcontroller in here. That's the AT Tiny 85. Great. So those are AT Tiny 85, and I believe everyone here remembers our old friend here, AT Tiny 85 microcontroller. We worked with it in our introductory session, and yeah, we made some very good progress. So that's also a microcontroller, right? So AT Tiny 85 microcontroller, and then we have the Atmega 328 microcontroller. Good. So these are the two microcontrollers we are going to be looking at in today's session. But yeah, let's go straight into the pin out. And a pin out is just these pins here, what they are used for, right? What they are used for. If this is used for power, if this is used for ground, if this is an input output pin, PB4, PB3, PB5, those, that is what we call pin out. And so quickly, let's take a look at, first let's take a look at an Atmega 328 microcontroller, the one found on the Arduino board. Oops, looks like this is quite tiny. I believe we are unable to see this really well. Give me a thumbs up if you are unable to see this really well. Give me a thumbs up if you are unable to see this really well. If it's very tiny. All right, this is very tiny. All right. We are on all right. So, all right, this is very tiny. But I believe everyone here, I believe the majority of us, everyone, I believe you have made it you've made it a point to join from your laptop so that you see everything really well. But yeah, so at Mega, let's just magnify it a little bit. Let's just magnify it. I believe everyone is able to see it bigger now. I believe everyone was able to see it a little bit bigger now. Give me a thumbs up. All right, so let's go back. It looks like it went off. So let's go back, and yeah, let's magnify it. Good. So this is an Atmega 328 microcontroller, and the pin out, the names of the pins, what the pins are used for, right? So these are the pins. We have one pin here called reset, right? We have a pin here called PD0. We have a pin here called PD1, PD2, PD3, PD4. Do not get scared about the names here. Like when you see PD4 and then you say and then you are scared. What is this used for? Do not worry about them. Just pay attention to what is written here. It may even get worse when you see ADC5, ADC4, and all of these things. But do not pay attention to all of them. Do not pay attention to all of the pins, right? Just pay attention to what we are focused on for today's session. And yeah, from our introductory sessions, we've taken a look at microcontrollers and we have classified the pins, right? We have the power pins. If you buy a computer, you need to give it power in order for your computer to turn on. And so we have the positive terminal, which is labeled as VCC here. We have the negative terminal, which is labeled as ground, right? And we may have multiple grounds. We may have different, we may have about 2 or 3 negative terminals. It's just one single negative terminal. They are all the same, right? So ground, we have negative terminal and we have positive terminal. So that is power. So we have power pins on a microcontroller. Good. And then we have input output pins. So they are called general purpose input output pins. They are called GPIOs. I think let's put that into the chat. GPIOs. So let's put that into the chat here. GPIO, right? Yeah, so GPIO and then just S for plural. So general purpose input output pins. So they are just input output pins that perform general purposes. So that's why it's called GPIO. So nothing too serious here. It's just general purpose input output pins, GPIO. So yes, we have the power pins. Let's magnify it once more. Let's magnify. Great. So we have the power pins, we have the positive, negative, that's power pins. We have general purpose input output pins, GPIOs, and that's where those are input output pins. That's where we connect our input devices and our output devices. So if you have an LED or a motor, those are output devices. We send signals into them, right? So those are output devices. And then we have input devices, like when you have a sensor, you need your sensor to send its values into the microcontroller. So you use input pins, right? So generally we have power pins, we have input and output pins. Oops, looks like we have a hand raised. Yes, Bernard, do you have a question? Do you have a question?
Hello, sir. You keep saying let's magnify it and all that, but we are still seeing from the search. We are not able to see the big screen
Oh,
itself.
all right, all right. So it looks like it's showing here on my screen, but it's not showing on your screen. But I think we can take care of that quickly. Let's just increase. Okay, let's choose a different image and let's see if that is going to increase for us. Oops, that's still same. But what we can do is let's just increase the yeah, let's just increase this here. But I think I have this downloaded. Otherwise, let's do this. Let's click on control and then I just use our cursor. Let's just um increase the size. All right, I believe now it's increased. I believe now it's a bit bigger now. We're able to see it. Okay, it's not stable. Let's just make it a little bit stable. 175% increase. All right, all right, I think this is good. Are we able to see it now? Give me a thumbs up if it's a bit bigger now. Give me a thumbs up if the image is now okay. All right, all right, all right, great, great, great. So yeah, our time is fast, man. Our time is left with just a few minutes. Let's quickly do this. So we have the power pins. We have negative terminal, positive terminal. That's oh, come on. All right. Okay. All right. I believe that's let's decrease a little bit. Yeah, I think this is good. This is good. We are able to see it, right? Yeah, this is good. All right, so we have the power pins, the negative and then the positive, and then we have input output pins or GPIOs, general purpose input output pins. Looks like we still have a hand raised. Yes, Felix. Yes, Felix. Please unmute. All right, all right, all right. That's great, great. All right. So yeah, okay. I think that's better now. All right, so that's the Atmega microcontroller. That's the Atmega 328. So we have the power pins, negative and positive, and then we have general purpose input output pins, GPIOs. So those are input output pins. Good. And then we have communication pins. Communication pins. So that's where our aim for today comes in. That's where your aim of understanding microcontroller communication comes in, right? So let's take a look at we're going to be taking a look at we're going to be taking a look at three communication protocols. We may not be able to go into detail in today's session because our time is up. We may not be able to go into detail, but I want everyone to just take note of the communication protocols we're going to be taking a look at in next week's no in tomorrow's session. So let's just create a new tab here, right? Let's just add another slide here, and yeah, let's do this quickly. So communication protocols, communication protocols, right? Communication protocols, good. And then we have one communication protocol is what we call UART, right? It's called UART, UART, and the full meaning of that is universal. The full meaning of that is universal asynchronous chronous yeah, universal asynchronous um um okay, UART, yeah, universal asynchronous what is that? Let's see, what is the RT? I've forgotten that. I've forgotten about that one. But for the second type of communication protocol, we just come back to UART, universal asynchronous, yeah, receiver transmitter. So that's so simple. Universal asynchronous receiver, right? For the R, receiver transmitter. So transmitter. That's great. So universal asynchronous receiver transmitter protocol. So that is UART. And then the second one is I squared C. I squared C. And usually it's mentioned I2C, right? I2C. So let's use capital letters for that. I2C. And the full meaning of that is inter, just as we have I2 there or I squared there, it means we have two of the i's, right? We have one I and we have another I, right? So that is simply integrated, right? So two of the i's, one of the first I stands for inter and the second I stands for integrated. So inter integrated, inter integrated, and the C stands for circuit, right? The C stands for circuit. So remember, just a minute ago we were discussing oops, looks like everything is very very tiny, but just bear with us. Everyone is going to appreciate this. But yeah, just a minute ago we mentioned integrated circuits, right? So the components that are black on the on an electronics board, and they have multiple pins. So those are integrated circuits, right? Now, if you want those integrated circuits like microcontrollers, those charging ICs, and other microcontrollers like the ones used for motor control and all of those things, if you want those integrated circuits to communicate together, that's when we use this particular communication protocol. And think of communication protocol as just a language, right? So if I go to the northern region, I will have to speak I'll have to speak a native language, right? If I go to Enzima, I need to speak Enzima. I need to speak a native language. If I go to the Ashanti Kingdom, I need to speak Tree. I need to speak a certain language, a native language. If I go to, yeah, so those are languages, right? Or communication protocols. It's just something like a language, right? Something like a language integrated circuits understand. So those black components, they need to communicate together. And in order for them to communicate together, they use this inter-integrated circuit. So it's like, we have inter schools, right? Those games, those sports games that used to happen in high school, or any school. So you have GSDS, you may have GSDS, you may have any all of the other schools, and just different schools, they are playing together, so inter schools, right? So that's just, you have multiple schools, and they are relating together, they are speaking with one another, or they are having fun with one another. So that is it. So for these integrated circuits, for these ICs like microcontrollers, on your TV's board, your TV's electronics board, or your laptop's electronics board, those integrated circuits, they need to communicate together, and they can use the first communication protocol called UART. They may also use the second one that we have written down here, inter-integrated circuit. So you have integrated circuit here as IC, right? And then you have inter here. So it's just integrated circuits talking with one another. So that is integrated, right? Inter, right? Yeah. So that's it. And then we have the third one, that's SPI, and the full meaning of that is serial peripheral interface. Looks like someone wants to join. Let's just admit him or her, and okay. Or was it a hand? Was it a hand that was raised? Okay, looks like that person is off. Okay, I think we can proceed. All right. So yes, so we have UART, that's a communication protocol. We have we have I squared C, or I2C, inter integrated circuit, and we have SPI, serial peripheral interface. So these are three communication protocols that are used in electronics, and in our next sessions, we are all going to appreciate this really well. Now, that's great. I believe everyone has made some good progress today. If you've made good progress, if you've learned something new, just give me a thumbs up if you've made some good progress in today's session. All right, Bernard, Agnes, that's great. Felix, all right, Abdul Salam, Felix, Samuel, Benedict, and Tim. All right, that's great. Samuel Entry, Michael Opoti, have you made some good progress in today's session? All right, that's great. Isaac, have you made, Herbert, have you made some good progress? All right. On this note, let's take a few questions. If you have any question, I believe our time is fast spent. But if you have, let's just allow for just a question. If you have a question, just raise your hand, and you'll be allowed to unmute and ask. Question. All right. I believe everything was simplified. And in our next session, God willing, tomorrow, we are going to be proceeding. But on this note, let's bring today's session to a close. Let's all have a very wonderful evening. And we're going to be connecting, God willing, tomorrow. Bye, everyone. Bye.